Jai Hind I am from Indian Space Team PR Department. Today's we discuss about orbit and rotation Earth-Moon system of Earth. Have you ever wondered why we have day and night? A simple question, yet the answer is as fascinating as it is complex. Let's embark on a cosmic journey to understand the spinning sphere we call home, Earth. Our planet performs a celestial ballet, rotating on its axis while also orbiting around the Sun. This rotation is what gives us our day and night. But the dance is not as straightforward as it might seem. Earth's rotation period relative to the Sun, known as its mean solar day, is not a neat 24 hours, but rather 86,400 seconds of mean solar time. And here's a mind-boggling fact. Due to a phenomenon known as tidal deceleration, each day varies slightly in length, anywhere between 0 and 2 milliseconds longer than the mean solar day. But the plot thickens. Let's delve a little deeper into the celestial mechanics. Earth's rotation period relative to the fixed stars, its stellar day, is slightly shorter than the mean solar day, clocking in at 86,164.0989 seconds of mean solar time. That's about 4 minutes shorter than 24 hours. Now let's introduce another term, the sidereal day. This is the time it takes for Earth to complete one rotation relative to distant stars, which is about 4 minutes shorter than our 24-hour day. This difference is due to Earth's motion around the Sun. So the sidereal day is shorter than the stellar day by about 8.4 milliseconds. These subtle differences in Earth's rotation might seem inconsequential, but they have significant effects on our planet and our daily lives. They influence everything from our timekeeping to the movement of our oceans and even the very climate we experience. So, the next time you watch a sunrise or a sunset, remember the intricate cosmic dance that makes it possible. Remember, it's the Earth's spin that gives us our daily cycle of day and night. But Earth doesn't just spin on its axis, it also dances around the Sun. This celestial waltz we partake in brings us to the third position in the solar system's lineup, nestled comfortably between Venus and Mars. We are part of the inner solar system, a bustling neighborhood of rocky planets, asteroids, and the fiery heart of it all, the Sun. Our Earth, the seasoned dancer, maintains an average orbital distance of about 93 million miles from the Sun. Imagine if you could drive your car straight up into the sky at 60 miles per hour. It would take you almost 200 years to reach the Sun. It's a distance so vast that it's been used as the basis for the astronomical unit, a standard measure in space science. This cosmic dance is not a quick step. It's a slow, graceful rotation around our solar partner. We take our time, making each full circle in roughly 365.25 days. That fraction of a day might not seem like much, but it adds up over time. And every 4 years we have an extra day in February, a leap year. As we twirl around the Sun, our tilt or axial obliquity plays a crucial role. At an angle of about 23.44 degrees from perpendicular, this tilt gives us our seasons. As we dance around the Sun, different parts of our planet get different amounts of sunlight throughout the year. This varying amount of sunlight gives us our winters and summers, autumns and springs. Without this dance, our Earth would be a very different place. No changing seasons, no variety in weather, and a year that doesn't quite add up. Our journey around the Sun is not just a dance, it's a delicate balance, a cosmic ballet that keeps life on Earth ticking along. It's this dance with the Sun that gives us our seasons and our year. But how fast does Earth travel on its cosmic journey, you may ask? Well, let's delve into the fascinating world of celestial speeds. The Earth, our home, is not just sitting idle in space. It's constantly moving, orbiting around the Sun. To be precise, Earth's orbital speed averages about 29.78 kilometers per second. That's a whopping 107,200 kilometers per hour. To put that into perspective, it's over 66,600 miles per hour. Yes, you heard that right. We're all moving that fast right now. But what does this mean in real terms? Let's consider the Earth's diameter, which is approximately 12,742 kilometers. At the speed we are orbiting the Sun, we could travel a distance equal to Earth's diameter in just 7 minutes. That's less time than it takes to brew a pot of coffee. Imagine being able to travel from one end of the Earth to the other in the time it takes to scramble your morning eggs. Now let's talk about our celestial neighbor, the Moon. It's about 384,000 kilometers away from us. With our orbital speed, we could cover this distance in about 3.5 hours. That's about the duration of a long movie or a Major League Baseball game. However, it's important to remember that we don't actually feel this speed due to the vastness of space and the lack of friction. It's like being in a car on a smooth highway. You don't feel the speed unless you look out the window or there's a bump in the road. So while we may not feel it, we're all moving at breakneck speeds on this spaceship we call Earth. But what about our closest celestial neighbor, the Moon? The Moon and Earth perform a cosmic ballet, orbiting a shared center of gravity, known as a barycenter, every 27.32 days relative to the backdrop of stars. This dance is more than just a twirl in space. It's a complex choreography that influences the rhythms of life on Earth. Imagine a line drawn from the center of the Earth to the center of the Moon. The barycenter, the point around which both bodies revolve, doesn't sit at the Earth's center. Instead, it's located about 1,700 kilometers beneath the Earth's surface. This off-center location is why our planet has a slight wobble as it spins on its axis. Now let's talk about the synodic month, the time it takes for the Moon to return to the same phase, say from new moon to new moon. Because of the Earth-Moon system's shared orbit around the Sun, the synodic month lasts 29.53 days. The Earth, the Moon, and their axial rotations are all counterclockwise if you're looking down from the celestial North Pole. But things get a bit more complicated when we consider the tilt of our planet's axis and the Earth-Moon plane. Earth's axis is tilted at roughly 23.44 degrees from the perpendicular to the Earth-Sun plane, the plane that describes our planet's orbit around the Sun. This tilt gives us our seasons. The Earth-Moon plane, on the other hand, is tilted up to plus or minus 5.1 degrees against the Earth-Sun plane. Now, why does that matter? Well, without this tilt, we would experience an eclipse every 2 weeks. We'd alternate between lunar eclipses, when the Earth blocks the Sun's light from reaching the Moon, and solar eclipses, when the Moon does the same to us. And that's why we don't have an eclipse every 2 weeks. So, how far does Earth's gravitational influence reach? Well, to understand this, we need to explore the concept of the Hill sphere. The Hill sphere is essentially the region around a celestial body, in this case Earth, where its gravity is dominant over the gravitational forces of more distant celestial bodies. Imagine a sphere drawn around our planet, extending into space. This sphere represents the extent of Earth's gravitational reach. Now, this isn't a fixed boundary like a wall or a fence. It's more like an area of influence, where Earth's gravitational pull has the upper hand. The radius of Earth's Hill sphere is approximately 1.5 million kilometers. To put that in perspective, that's about 10 times the distance to our Moon. That's right, our gravitational influence extends far beyond the Moon, reaching out into the depths of space. So, what does this mean in practical terms? Well, any object that falls within this sphere is more likely to be influenced by Earth's gravity than by the gravity of other celestial bodies, such as the Sun or other planets. This is why the Moon, which orbits within our Hill sphere, is held in Earth's grasp. But the Hill sphere is not a solid barrier. It's more of a gravitational tug-of-war zone, where the forces of Earth and more distant celestial bodies vie for control. Objects that venture too close to the edge of the Hill sphere could potentially be pulled away by the gravitational forces of other celestial bodies. In conclusion, Earth's gravitational influence extends far beyond its visible boundaries, reaching out to touch the cosmos. Our planet's gravitational pull shapes the paths of moons, satellites, and even comets that pass by. This invisible sphere of influence, the Hill sphere, is a testament to Earth's presence in the vast expanse of space. So, while we might seem small, Earth's influence reaches far into the cosmos. Share this video for more knowledge about space.